Hi everybody, this is our lecture on section 2.4, which is on the cross product. So the cross product U cross V is only defined for two three-dimensional vectors only. This is unlike the dot product, which is defined for 2D and 3D vectors. Okay, but before we define the cross product, we need to go over some preliminary ideas. So start with determinants. And there's two types of determinants that we're going to be interested in. First of all is a 2 by 2 determinant. So if you have this 2 by 2 array of real numbers, then the 2 by 2 determinant, that's the array with these bars around it, is the product AD minus BC. And you can think of it kind of like this. It's the forward product, the down and forward product, minus the down and backward product, right? AD, BC. And this is AD minus BC. So the forward and down product minus the backward and down product. Okay? And then a 3 by 3 determinant is defined as follows. So you have a 3 by 3 array A, B, C, D, E, F, G, H, I. So this is equal to A times E, F, H, I minus B times D, F, G, I plus C times D, E, G, H. And I'll show you a way to remember that. Take the 3 by 3 determinant here, that symbol, okay, and then the first term here, so you start with the top row, right? We have this A here times this 2 by 2. So here's the A. Cross out the row and column for A, and you're left with the 2 by 2, E, F, H, I. Then we got the B here. Cross out the row and column for B. Then you have D, F, G, I, which is that 2 by 2 right there. And then you have the C. Cross out the row and column for C. And then you're left with the 2 by 2, D, E, G, H, right, which is that 2 by 2 matrix or determinant there. So that's a sort of graphic way to remember what the 3 by 3 determinant is. Now, if you take matrix algebra or differential equations with matrix algebra, then you'll learn more about the determinant. This is a very, very rudimentary, sort of rough and ready definition of determinant, and it doesn't really begin to scratch the surface of what the determinant really is or what it really means. Okay, so for example, if I've got this here, 4, 2, 1, 1, 0, minus 1, 0, 2, minus 3, then that 3 by 3 determinant is 4 times the 2 by 2, like that, minus, not plus, but minus, so it's plus, minus, plus. 2 times the 2 by 2 determinant, 1, negative 1, 0, minus 3, plus c, which is a 1, times the 2 by 2 determinant, 1, 0, 0, 2. So this is equal to 4 times 0 plus 2. Right? It's 0 minus minus 2. Minus 2 times minus 3 minus 0 plus 1 times 2 minus 0. So this is equal to 8 plus 6 plus 2, which is 16. Okay, so that's that 3 by 3 determinant. So now the dot product of u and v, or not dot product, cross product, given u equal to a1, b1, c1, and v equal to a2, b2, c2, define the cross product u cross v as follows. So u cross v is equal to the 3 by 3 determinant, where on the top row I have I, j, and k. Second row is u. Third row is v. And this is equal to the three-dimensional vector whose x component is this 2 by 2 determinant, right? We cross out the row and column for x, and we get this determinant, b1, c1, b2, c2, and then whose j component is this 2 by 2, negated. The negative of the 2 by 2, a1, c2, c1, a2, a1, c1, a2, c2, and then the k component, right, is going to be this 2 by 2 determinant, a1, b1, a2, b2. So, for example, the cross product of 1, 0, 2 cross minus 5, 1, 1 is equal to, so we write down the determinant, ijk, first vector, and the second vector. So this is equal to the 2 by 2 the vector of 2 by 2 determinants as such. So this one is equal to 0 minus 2. This one is 1 plus 10. This one is 1 minus 0. Okay, so, oops. 1 plus 10, so it's 1 minus minus 10 is 11, but then I got to negate it. So then I have minus 2, minus 11, 1. Okay? Some algebraic properties of the cross product are as follows. One, it's not commutative. U cross V, if you did the other way around, V cross U, it's the negative of it. So it's not commutative. It's kind of like, right, how subtraction behaves, right? 3 minus 5 is minus 2. 5 minus 3 is positive 2. So it's a non-commutative operation, but it's non-commutative in a very sort of predictable way. 2, if you take a scalar times U, cross it with V, it's the same as taking U, crossing it with KV. It's the same as multiplying U and V, cross product of U and V, and then multiplying by K. The cross product also distributes over addition. And for U cross the 0 vector is going to be, again, the 0 vector. More generally, U cross V is 0 if and only if U and V are parallel. And we'll see why that's the case in just a moment here. Another example of cross products would be the following. If you take those vectors I, J, and K and arrange them like this in a triangle, sort of rotating in the clockwise direction. If you did the cross product of I and J, it would be equal to K, which is going to be equal to the negative of J cross I. If you actually calculated it, you would find that I cross J is K. Right? I cross J is K. So we're going in the direction of the triangle, so the cross product of the two is the third. If I'm going J cross I against the direction of the triangle, the cross product is the negative of the third. So I cross J is K, J cross K. J cross K is I, K cross J is negative I. K cross I is J, which is the negative of I cross K. So if you were to actually do the determinant, right, I, J, K, 1, 0, 0, 0, 1, 0, right, this is I and J. If you were to calculate this by hand, you'll see that it's K. So it's this 2 by 2 determinants, which is 0. And that one's 0, and then 1, 0, 0, 1. So you get 0, 0, 1. So I cross J is K. Okay, so, I mean, you'd have to check it, but, we'll just take that as known at this point. All right, so that's the component definition of the cross product. You have two vectors, you know what their components are. Now you know how to calculate the cross product. But it doesn't give us any geometric meaning to what the cross product is. With the dot product, we did the other way around. We started with the geometric meaning of the dot product, and then we derived the component definition, the arithmetic definition after that. So here we're starting with the arithmetic definition, and we are going to talk about the geometric meaning, although we're not going to prove it because it's just kind of a little bit long. Okay, so the theorem is as follows. U and V are both perpendicular to U cross V. The direction of U cross V is given by the right-hand rule. So it looks like this. Here's U and here's V. I'll put it here. Right, so here's a vector that's perpendicular to both V and U. Right, so there's only two choices of direction. Right, this way and downward. So this one is U cross V, and I'll tell you why. And then this one is V cross U. It's the negation of U cross V. And how do you get that? You use the right-hand rule. Take your right hand, even if you're lefty, take your right hand, okay, and curl your index fingers, curl your four fingers in the direction from U to V. I mean, it's easier if I could show you in person, but you know, sort of gently curve your fingers, four fingers, and curve them in the direction from U to V. Now your thumb will give you the direction for U cross V. Right, so if I curl my fingers in the direction from U to V like this, so here's fingers 1, 2, 3, 4, there's the rest of my hand. Now my thumb is pointing upward. So that's U cross V. So then V cross U is in the opposite direction. I curl my fingers in the direction from V to U. Right? Curl my fingers in the direction from V to U. And then, try to draw that. 1, 2, 3, 4. And then here's my thumb. And there's my wrist. So there's my right hand, right, with my fingers going in that direction. Well, that's not too horrendous, is it? It's not what I meant by, you know, improving your artistic skills in this class. Eraser. Alright, so I've got my index fingers curved in the direction from U to V, and then my right hand and my thumb points in the direction of U cross V. Alright, and then the other one, V cross U, if I curl my fingers the other way, I'd have to turn my hand upside down with my thumb pointing down. Okay, so that's the two facts. U and V are both perpendicular to U cross V. And the direction, one of two directions, is given by the right-hand rule. And then the length of, so we know what the direction is, and then the length of U cross V is much like the dot product. It's, instead of UV cosine theta, this one is UV sine theta. the length of u cross v. Now the dot product of u dot v, the dot product is a real number. Right, u dot v was equal to u v cosine theta. Right, it's equal to that. Here, it's not u cross v, it's the length of u cross v. The length of u cross v is equal to this, right, which is sort of very close to that, related to that. But this is u dot v itself rather than the length of u and v, rather than the length of u dot v. Here, it's just the length of u cross v. So we've got the length and we've got the direction. Now, I'm not actually going to prove this. We're just going to take it for granted. You can, I think it's in the book, or you could look it up. I'm sure you could find any number of proofs about it, but it's just a little bit much to go over right now. Also, given u and v, you've got this parallelogram u v like that. Right, if you remember, you can put copies of u and v above and below like that. Right, so this is u and this is v, and they create this parallelogram. Now, if I took the height of this parallelogram, it's this line right here. So if this angle here is theta, and then this is a perpendicular, this red length here is the length of u times sine theta. So the base of the parallelogram is the length of v, and the height of the parallelogram is the length of u times sine theta. So the area of the parallelogram is equal to base times height, which is equal to the length of u, length of v, sine theta, which is equal to the magnitude of the cross product. So the area of that parallelogram is encoded by the cross product. Again, pretty neat. Right? You don't have to fuss with sines and cosines in order to calculate the area of that parallelogram. We don't need to do any angle calculations. It's built into the cross product, the component definition of the cross product. So, for example, let's find the area of the triangle. So if I've got these two vectors here, and we'll call this, let's actually do this. So here are 3 points in three-dimensional space. We'll say this is 1, 1, 1, negative 1, 0, 1, and 0, 2, 1. Let's find the area of this triangle. Okay, well, copy the triangle. And now let's pick two sides to be vectors. So this vector, head minus tail, is minus 2, minus 1, 0. This vector head minus tail, minus 1, 1, 0. Well, not me. Oh, maybe I'll make that different. 1, 3, 2. So now this is 0, 2, 1. So now I've got these two vectors here. Now the area of the triangle is half the area of the parallelogram given by these two vectors. So the area one half the area of the parallelogram, right, which is one half the length of the cross product. So this is one half, and then the cross product is I, J, K, minus 2, minus 1, 0, 0, 2, 1. And we're going to calculate the length of that cross product when we're done. So one half the length of the cross product. So in the x component, we have minus 1, minus 0. In the y component, minus 2, minus 0, which is minus 2, negated. And in the z component, we have minus 4, minus 0. So 1 half the square root of 1 plus 4 plus 16 is root 21 over 2. So that is the area of that triangle, and that is pretty neat. So you've got a triangle in 3 dimensions. You just specify these 3 points, and you can calculate the area of that triangle just by calculating the associated cross product. Now notice that you have to pick 2 sides to be the vectors. I picked this side and this side. It doesn't matter which sides you use. Okay, I could do this side and this side, or this side and this side, or this side and this side. Whatever 2 sides you pick, and whatever directions you pick on those 2 sides, the cross product changes, but the length of the cross product doesn't. Okay, so by the way, let's also check that the cross product is perpendicular to the first 2 vectors. So in the last example, we calculated that minus 2, minus 1, 0 cross 0, 2, 1 is equal to minus 1, 2, minus 4. Okay, notice that minus 2, minus 1, 0 dot product minus 1, 2, minus 4 is equal to minus 2, or sorry, plus 2, minus 2, plus 0, which is 0. And the other one, 0, 2, 1 dot minus 1, 2, minus 4 is equal to 4 minus 4, which is 0. All right, so they're both perpendicular. All right, the cross product U cross V is perpendicular to U and perpendicular to V. You can prove that more generally, but you know, we're just going to take these geometric facts about the cross product for granted, just in the interest of time. If I had more time, I would go over why it's the case, but you know, it's fine. So what's the usage in? So the usage of the dot product in physics is for measuring work. What is the usage for cross product? Cross product is used for measuring something called torque. All right, so in physics, torque is a force producing rotation about an axis. And then this rotational force, the torque, is a vector parallel to the axis of rotation in 3 dimensions. So the idea is as follows. You've got this lever. This lever vector here. And, you can sort of extend that vector out this way. Let's use dashed lines. And then you can make a perpendicular thing there as well. Now, if I had a vector in this direction, a force vector, this is a lever vector, and then this is a force vector. If I had a force vector parallel to the lever, it's not producing any rotation, right? No rotation at all. If I have a force vector perpendicular to the lever vector, well, yeah, that's giving me good rotation, right? I mean, anyone's ever used a wrench before knows you push a wrench perpendicular, with your hand. You use your hand perpendicular to the wrench, if at all possible, if you can get your hands in the right position, right? I mean, you don't pull on the wrench, you push on it. Sorry, you don't pull it in the direction of its handle. You push or you pull the wrench perpendicular to its handle. So if I've got a force vector that is not perpendicular to the wrench itself, okay, what part of that force vector is perpendicular and what part isn't? So if I drop down perpendicular this way and that way, this length right here is length of F, and if we've got a theta in here, I'll get rid of that. If I've got a theta there, this length right here is F cosine theta. This length right here is length of F sine theta. Length of F sine theta that's the part of the F that's going to be producing rotation, right? Just that part of the force, right? I mean, you would like that your force is itself perpendicular to the lever that you're using to produce rotation over here. You would like that it was perpendicular to begin with because, this bit of the force is wasted. And the other bit, the parallel bit is wasted. The perpendicular part is the only one that's useful for producing rotation. That's better. But if it's not, then this is the part that you're using. Okay, so the amount of rotation. So the magnitude of the torque. Okay, well, the longer your lever, the better, right? I mean, if you've ever used a breaker bar, I mean, what's a breaker bar? You got a stuck bolt somewhere. Typically on somewhere on your car or something like that. You get that big old like 2 foot wrench, right? And you put that wrench on the bolt, and then you push it, and then that gives you a lot more force. The longer the wrench, the more force. The longer the lever, the more torquing force you get. It doesn't matter how strong you are, as long as that lever is long enough and stiff enough, it'll give you enough torquing force to break that bolt, get it moving, right? Or just break the bolt itself. So it's the length of L times the length of F times sine theta. So the force of the torque is that, right? Which is equal to the length of U cross V. Or not U cross V, but F cross L. Right, and then what would be the direction for the torquing force? what would be the direction for the torquing force? Well, I mean, the lever is going in a circle. So any direction that's in that circle doesn't make sense. Right? Any tangent to that circle, any direction along that circle doesn't make any sense for the torque because that's only the torque at one part. Right? So a torque going north, a torque going east, south, west, whatever, doesn't work. The only direction for the torque that's possible is perpendicular to both F and L. It is perpendicular. Right, so torque is perpendicular to both F and L, and its length is the length of the cross product. So the torque vector itself is equal to F cross L. So force cross lever. Pretty neat. Okay. So that's the end of the lecture on this section.